everybody, this is Dr. Nigro with the Chem Calculations screencast. This screencast is going to look at how to calculate the change in enthalpy for a chemical reaction utilizing bond dissociation energy values. All right, there are many different ways to determine the energy of a reaction. We could use something in the lab. We can use a calorimeter to look at the energy exchange between that process and its surroundings. We could also use the energy values of the formation of certain substances and calculate it that way. Another way is to look at the energy required to break the bonds and compare that to the energy required to form bonds when we have a chemical process taking place. So that is what we're going to look at here. All right, so that energy of a reaction, right, which we call the change in enthalpy of that reaction, all right, can be determined by comparing the energy needed to break reactant bonds to the energy needed to form product bonds. All right, so we can write that as a formula. The enthalpy change for a particular reaction is going to be equal to the sum of the bond dissociation energy values for your reactants. So these are our bonds. Well, actually, maybe instead of reactants, let me write, broken. And this is going to be, maybe this is a better way to say it, your reactants minus the sum of the bond dissociation energy of the bonds that are formed. And this is going to be your products. All right, now normally when we think of change, we think of the after minus the initial. This is one of the rare times where it really seems to be flipped because we talk about reactants minus products. All right. To work these problems, there are a couple things you have to do before you even get to the numbers. All right, the first thing, you got to balance. All right, I know I say that for everything, but you really have to do it here. So you need to balance that chemical reaction. All right, second, all right, you're going to have to draw Lewis structures of all compounds. All right, and they need to be correct because you're going to be looking at bond types and the number of bond types within each compound and then adding all that stuff up. So if you mess up your Lewis structure, then you are going to have a problem. All right, for a third step, this is one I like to do. It's not required. All right, I say that you look at those structures and you tally up the bond types and number of each type. And then once you have that done, you plug in your values and solve. All right, so we're going to do two examples. All right, we're going to go through each one of these 4 steps. And then I have the bond dissociation energy. I have a table next to me on my desk. I also have put a link right here on the top. So you could click this and it will take you right to a particular bond energy table. You can see that I've got a lot of different bond energies here. You can also Google a particular bond. Just keep in mind, all right, that you Google the right bond, the right 2 atoms that are being connected, and that you keep an eye out for the multiple bonds. All right, if it's a carbon-carbon single bond, its bond dissociation energy is going to be very different than a carbon-carbon double bond or a carbon-carbon triple bond. And that goes for any of the elements. All right, so let me switch back over here. Whoops, sorry. Sometimes things disappear. There we go. All right, so we're going to start with balancing. All right, so let's see. I've got 1 carbon and 1 carbon, 4 hydrogens, 2 hydrogens. So let's start there. All right, that's going to give me 4 oxygens plus 2 oxygens plus 4 total. Oh, but I have 3. All right, so that's not going to work. So I'm going to need 2 of my first substance to get an even number of oxygens on both sides. which means I need 2 CO2s for those carbons. And now I have 6 plus 2 more, 8 hydrogens. So I'll need 4 waters, which is going to give me 4 oxygens plus 4 more is 8. 2 of them are in my methanol, which means I need 6 more, so 3 O2 molecules. All right, so please make sure you balance first. If you don't balance first, then you are going to have a problem. All right, so here's my balanced reaction. Now, Lewis structures. All right, so methanol, so I've got a carbon with a hydrogen, and a hydrogen, and that carbon is also attached to an oxygen, which is attached to another hydrogen. All right. If I look at my Lewis structure, my carbon has an octet, so that's great, but my oxygen needs 4 more electrons. So I'm going to put in 2 lone pairs, and then the hydrogens all have their duet, which is good. All right, now for the molecule itself, for valence electrons, I had 4 from the carbon, 4 more from the hydrogen, so that's 8, plus 6 from my oxygen. So I had 16 valence electrons to work with. And my structure shows 2, 4, 6, 8, 10, 12, 14. What? 2, 4, 6, 8, 10, 12, 14. What? My math is bad. What did I do wrong? 4. What did I do wrong? 4 carbons plus 4 hydrogens. That's 8. Plus 6. Oh. Yeah, that is 14. Sorry. My students, when I work problems at the board, often have to help me because my simple math sometimes is not what it should be. All right, so if I count now, I show 14 electrons in my Lewis structure, so I know this is a good structure. All right, but I have 2 of them. Sorry about that, my friends. There's usually not anybody in here this time of day, but I guess there is today. All right, now to that, I'm going to have 3 O2 molecules. So oxygen is going to be bound to another oxygen. I have a total of 12 electrons to work with. All right, but I don't have enough electrons with the bond, so I'm going to need a double here. Lewis pairs, lone pairs, sorry, around those oxygens. So I'm going to get this structure. All right, those are my 2 reactants. Now I go over to my product side. I have 2 CO2 molecules. All right, so that's an oxygen with a carbon with an oxygen. All right, I'm going to have a total of 4 plus 12, so I have a total of, now that is 16 electrons, and I don't have enough. So I'm going to put 2 doubles in here and then lone pairs. Right, now, when you practice your Lewis structures as many times as I have, some of these you remember. All right, now I've got 2, 4, 6, 8, 10, 12, 14, 16 electrons showing, so that's a good structure. All right, then I'm going to end with my 4 water molecules. All right, so I've got a hydrogen attached to an oxygen attached to a hydrogen. All right, so I have 6 plus 2, 8 valence electrons to work with. 2, 4, 6, 8. There they are. All right, so these are my Lewis structures. Also a vital step. All right, now the tally step. All right, so the enthalpy change of the reaction is going to be equal to the sum of all the bonds that get broken, so that's my reactant side, minus the sum of all of the bonds that get formed. All right, so if I look at my methanol structure, I have CH bonds, and I have 3 of them, but they're 2 molecules. So 2 times 3 is 6. So I'm going to have 6 CH bonds that I need to break. All right, in addition to that, I've got a CO bond. All right, but because I have 2 molecules, I have 2 CO bonds. All right, and then I also have 1 OH bond, but I have 2 molecules, so 2 OH, H bonds. All right, so that's for my first reactant. All right, for my second reactant, I have O2 molecule, which has an OO double bond. I have 3 of them. So I need to break 3 OO double bonds. All right, and that is my reactant side. On the product side, whoops, I need to subtract those. All right, I'm going to start with my CO2 molecule. All right, so here I have 2 CO double bonds, but I have 2 of the molecules, so I have 4 C double bond O's. All right, nothing else in the CO2 molecule. Now I move over to my H2O molecule. I have 2 OH bonds, but I have 4 of those molecules, so 2 times 4 is 8 OH bonds. All right, so this is the tally of what I need to break and then what I need to form. All right, so now I'm going to start plugging in numbers. And again, I took these off of that table that I linked above. You also could just look up on Google any of these or your textbook. All right, so the CH bond costs 413 kilojoules to break. All right, the CO bond costs 358 kilojoules to break. The OH bond costs 476 kilojoules to break. And then those three O2 molecules are each 498 kilojoules to break, minus 4 of those CO double bonds, 799. See that big jump because of that double bond? All right. And then I have 8 OH bonds, which is 467 kilojoules to break, or to form, rather. All right. So this is where we are in terms of our numerical values. Now we just need to plug it all in. Now I did this initially, but I did mess up one spot. So I'll have to catch that. 2, 4, 7, 8 for those 6. 716 for those. 952 for those. This is where I messed up before. I messed up my balancing, I'm sorry to say. And 1,494 for those. Then on this side, 3196 kilojoules and 3736. All right, so we're going to have 2478 plus 716 plus 52 plus 1494. So it's going to be 5,640 kilojoules to break the bonds. And from that, we're going to subtract out 6,932 to form the bonds. Now remember, the bond breaking is being absorbed, the bond forming is being released. All right, so when we finish, we actually get a negative value here of negative 1,292 kilojoules, which tells me that this process is exothermic. So it's going to release energy when the process occurs. Okay, now does that mean it's going to happen for sure? No. All right, but probably. All right, so we're going to move down to this second one. All right, we're going to do the same thing. We're going to start with balancing. So I have 2 carbons on the product side, 2 on the reactant side, 3 hydrogens on the reactant side, 4 on the product side. No, I got to fix that. 2 chlorines on the product side, 1. So let's put a 2 here, and that's going to fix my hydrogen problem too. All right, so let's start with our Lewis structures next. All right, so I've got a hydrogen attached to a carbon, attached to a carbon, attached to a hydrogen. So that's 4 plus 4 is 8, plus 2 more, so I have 10 electrons to work with. Well, I can't do anything else with the hydrogens, so I'm going to try a triple here. All right, it's going to be 2, 4, 6, 8, 10. So that's the structure right there. All right, now, according to my balanced reaction, I only have 1 of those. So that one's all set. All right, HCl is a diatomic molecule. So its Lewis structure just has the bond and then the lone pairs around the chlorine, but I have 2 of these guys. All right, now I'm going to move over to the one that looks a little different. All right, so I have a carbon and a carbon. All right, now I'm going to spread the hydrogens and chlorines out symmetrically around these 2 carbons. Does nature do it that way? Maybe. Sometimes, all right. If you take organic chemistry, you're going to learn that those chlorines can be in a bunch of different places. But the bottom line is they will not be in between any other atoms. So I just like symmetry. So I'm just going to do this. All right. If I look at the valence electrons available, I have 14 from my 2 halogens plus 4 more. That's 18 plus 8 more. So I have 26 electrons to use. I used up 2, 4, 6, 8, 10, 12, 14, which leaves me the ones I need. So I just fill in lone pairs around those chlorines. All right, now one thing to keep in mind, is that I only need 1 of those guys. All right, so we're all done with our Lewis structures. All right, so now we move on to our tallying. So our enthalpy of reaction is going to be equal to, we start over here with our C2H2, all right, we're going to have 2 CH single bonds. So 2 times CH bond dissociation energy plus, I'm going to have 1 CC triple bond. Whoops. And now I move to my other reactant, only a single bond in here, and it's a HCl bond, but I have two molecules, so I'm going to have to break two of those bond types. All right, so that's going to be my reactants. Now I move over to my products. All right, I have a couple different types of bonds in here. I have a ClC bond, a carbon chloride bond, and I have two of them. All right, and then I have HC bonds, and I have four of those. And then I have one last bond in here. Please don't forget this guy. All right, a carbon-carbon single bond. And I have one, whoops, what happened there? All right, so those are all the bonds that I have. All right, if you want, you can always check. All right, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different types of bonds. And down in our tally, we have 2 plus 1 is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they're all showing in our tally. So now we're going to put in values. The enthalpy change of the reaction is going to be equal to 2 times 413 plus 1 times 839 for that triple bond, and then 2 times 427 for the HCl bond, minus 2 times, oops, I did them in a different order, 339 plus 4 times 413 plus 1 times 347. All right, now, my students always ask me if I can cancel bonds. You can. You just need to be really careful that you don't mess up. So I tend to just leave them all in there. All right, so that enthalpy change for the reaction is going to be equal to 2,519 minus 2,677. All right, so the net is going to be 158 kilojoules per mole of energy being released. All right, so again, this is another exothermic process. So probably going to happen. But again, depends on some other factors, which we will get to when we get to thermodynamics, okay? All right, so just to reiterate, all right, the enthalpy change of a reaction can be calculated by looking at the bonds formed versus the bonds broken and the difference in energy in those two processes. Before you can do that, though, you have to balance your reaction. Then you must draw your Lewis structures of all the reaction components. And then I like to tally up the bond type and bond number on each sides of the arrow, then plug in my values and solve. But that doesn't mean it's the only way to do it. It's just, for me, the easiest. Okay?